All right, good morning, everybody. Welcome to JV Chemistry, Honors Chemistry. Today is March 31st, and today we're going to do a virtual lab, the standard molar volume of a gas. So we're going to start by sharing the screen so that we can all look at the agenda for today. Actually, let's look at the agenda for the week. So yesterday I left some gas stoichiometry practice for you to do. Hopefully you got a chance to take a look at that. I also left another gas stoich practice worksheet. Both of them were in the classroom. The answer keys are available for both of them too. So basically I'd like you to do as much of those worksheets as you deem necessary to help understand gas stoich. I also asked you to do a pre-lab in your lab book last night to work on this purpose, background knowledge, safety protocol for the standard molar volume of a gas lab. And so that was yesterday. Today, we're in our Zoom meeting right now. We're going to start with molecule of the week. I'll answer any questions that you have about the standard molar volume of a gas. I'm sorry, about the gas stoichiometry worksheet, and then we'll get into that virtual lab today. I'd like your lab report due tomorrow by 8 a.m., please. And I'd like you to submit that on Google Classroom the way you have been. Some of you are running into some hiccups. You might want to talk in your small groups today if you're having trouble submitting online, and see if anyone in your small group has suggestions for you on how to submit your work. Let's see, tomorrow I'm going to leave some exam review for you. As a matter of fact, I uploaded some exam review for you yesterday. So actually, let me share my screen a different way. If you go to Google Classroom, you should see a few new things in the classwork. There's this gases exam review with a key. So I'd like you to work on that tomorrow because we don't get to meet tomorrow. And on Thursday, we'll have another meeting. And my plan for that meeting on Thursday is just to answer any questions you have about gases in general. Anything that you have about the exam review or the lab or anything, you can ask me during the meeting. And then right after the meeting, I'll go ahead and open up the exam for you to do. The exam will be in the form of a Google form that you fill in. And so you can just take the gases exam that night or sometime Thursday afternoon. And then Friday, we don't have a meeting. So I'll make it so that you can see what answers you got wrong on your tests. And then if you have questions, you can always email me about it. But I would have loved to meet with you on Friday to discuss your results of your test, but we don't have a meeting on Friday. So you'll just have to review it on your own. And then if you have questions for me, don't hesitate to email me. And then you guys get a nice, relaxing spring break. Okay, I'm not going to give you anything to do over spring break. I think we've all been working very, very hard. So don't forget to come in over here on the attendance sheet and fill in your attendance. One thing, please do not look at this person answer. They filled themselves in advance. That's what I'm going to ask you not to do. Please do not fill yourself as being here in advance. You need to check in on a day-to-day basis. It's just like attendance at school. So go ahead and come on over here and put a P next to your name for today's date on Tuesday. Okay, but don't fill in advance. It's not too hard to come on over here and add a P next to your name on the days that you're supposed to check in. So, okay. Let's see what else here. Let's go ahead and start with our molecule of the week. All right, molecule of the week this week is luciferin. And luciferin is a molecule that's found in bioluminescent organisms. And when organisms emit light, it's because of this chemical that you see here. It's found in the light of fireflies and in deep sea fish as bioluminescence, such as the anglerfish, or even in plankton, like dinoflagellates that are capable of bioluminescence. And it's called luciferin. Does anyone recognize the word Lucifer, or can you tell me who Lucifer is?
The devil.
The devil, yeah. Lucifer is another name for the devil. And the reason why they named this molecule after the devil is because they thought that it was the work of the devil when these organisms were glowing. So it was actually discovered by Aristotle and Pliny the Elder. They noticed that damp wood gave off a glow that turned out to be foxfire, a certain type of bioluminescence that's found in the fungi of decaying wood. But yeah, these early scientists thought that the light was work of the devil, so hence they named it luciferin. But kind of cool, they can actually use luciferin to tag viruses. Speaking of viruses and our awful outbreak that's going on right now, I hope you all are staying at home. Anyway, they can use it to tag viruses in order to study how they act and caught in their cause of disease. So, all right, so there's your molecule of the week. Okay, next up is review for, oh, let's see, I see a question. Yes, Ella is asking me a question. Are we going to do the lab report in your lab book? Yes, the answer is yes. You are going to do the lab report in your lab book. And the reason why you're doing it in your lab book, Ella, is because you're going to repeat this lab next year in AP chemistry. Okay, next up was the gas stoich worksheets. So I put 2 worksheets up on Google Classroom for you guys to work on yesterday based on the concepts I taught you over, let's see, before the weekend on Friday. So they were this one, the gas stoichiometry worksheet, and the more gas stoichiometry worksheet. Did anyone have questions for me about either of those 2 worksheets? I'm going to unmute you all. You're all able to talk if you have questions. No? Nothing? Okay, well, you'll get to put those stoichiometry skills to work today with some lab data. Okay, so if you have questions, don't hesitate to ask or reach out to me. All right, and let's go on to the standard molar volume of a gas virtual lab. So I uploaded this and asked you to do the background knowledge and the purpose, background knowledge, and safety protocol last night. I also uploaded the rubric for you to make it nice and easy for you to write up this lab. I'm trying to make it as simple on you as possible. So let's go ahead and read the introduction together. Actually, do I have a volunteer to read this introduction so that somebody can hear someone else's voice beside mine?
I'll do it.
Great, thanks. I think that was Hannah.
Yeah.
Great. Whenever you're ready, Hannah.
Both solids and gases are often handled in the same experiment. The mass of a solid can easily be determined using a balance. However, it is more difficult to find the mass of a gas. Chemists measure gas volume and use this value to calculate the number of moles and furthermore the mass of the gas. Therefore, it is necessary for the chemist to know the quantitative relationship between the volume of a gas and the number of moles of the gas. Avogadro's hypothesis explains this relationship and states that equal volumes of gas under the same temperature and pressure conditions contain an equal number of molecules. This is the basis behind the standard molar volume of a gas. In other words, the volume occupied by 1 mole of any gas at standard temperature and pressure equals 22.400 liters.
Okay, so you guys remember this, right? It doesn't matter what the identity of the gas is. 1 mole of any gas under standard temperature and pressure conditions has a volume of 22.4 liters. And I'd like you all to get out your calculators. You're going to need your calculators today. So please go ahead and get those out. And I have a new little whiteboard set up here. Fell apart, but I'm hoping you guys can see this. All right, so let's take our ideal gas law, PV equals NRT, okay? Can you guys see that on the board there?
Yes.
Yes, excellent. Okay, I want to plug in conditions of STP, right? So let's think about what are the standard temperature and pressure conditions here. So P, V, N, T. What's the standard pressure?
20.
Standard
1 atmosphere.
1 atmosphere, right? Like at sea level, 1 atmosphere. And what's the standard temperature, students?
273 Kelvin.
273 Kelvin or 0 degrees Celsius, 273 Kelvin, right? We want to make sure that our units are all in the right units when we use Pivner, right? So we need atmospheres, Kelvin. And let's go ahead and plug in 1 mole per N. So if I have 1 mole of a gas under standard temperature and pressure conditions, and I plug and chug, let's see what happens. The pressure is 1 atmosphere. The volume is what I'm going to solve for. N is 1 mole. R is 0.08206 or 0.2810821. And the temperature is 273. I want you guys to plug and chug into your calculators and tell me, what do you get for volume? Guys, all of your calculators out.
22.4.
Oh my goodness, really? You got 22.4 liters? Aha! This is where that number comes from. It actually comes from Pivnert. Okay, so when I took standard temperature and pressure conditions, 1 mole of any gas at standard temperature and pressure has a volume of 22.4 liters. Now, does the identity of the gas matter?
No.
No, I didn't tell you whether this was carbon dioxide or nitrogen or oxygen or carbon monoxide or water vapor or neon or helium in my balloon. It doesn't matter what the identity of the gas is. 1 mole of any gas at standard temperature and pressure has a volume of 22.4 liters. And that's the goal of the lab today, is for you to figure out if this is true experimentally. Okay, and so that's what we would be setting out to do if we were back in our lab. So the purpose of this lab is threefold. Purpose number 1, or objective number 1, is to experimentally determine the volume of hydrogen gas collected from a reaction between hydrochloric acid and magnesium. 2, use the volume of hydrogen to determine the number of moles of hydrogen collected. And 3, compare your results to Avogadro's hypothesis at STP, which is called the standard molar volume of a gas. So we call this the standard molar volume of a gas because it's the volume of 1 mole of a gas under standard conditions. Hence the name standard molar volume. 1 mole, standard conditions, volume is 22.4 liters, okay? So let's start with the background knowledge. I think we should be able to answer these together. And I asked you guys to do them for homework last night, so hopefully you've already gotten a chance to take a look at them. But I'm gonna go ahead and go through it on the board here. So question number 1, write a balanced equation for the reaction between hydrochloric acid and magnesium metal. So Actually, let's do this. So this is the background knowledge. Okay, so hydrochloric acid plus magnesium metal. Hydrochloric acid, any acid or base will be aqueous. Magnesium metal is a solid. What kind of reaction do you think this is going to be?
Single reaction.
Yeah, single replacement reaction. Good. So hydrogen is going to get kicked out by itself. And then we're going to have magnesium and chlorine are going to dance. And magnesium chloride, according to solubility rules, is aqueous. Is this the formula for hydrogen?
No, 2 hydrogen.
No, hydrogen's diatomic and it's a gas at room temperature. So this is the gas that we're going to create. And then of course we need to balance it. Okay, and that's the chemical reaction you would be doing today. Okay, the evidence of a chemical reaction is going to be bubbling. All right, next, write the equation for Dalton's law of partial pressures for gases collected over water. So we've already seen this one a couple of times. Remember that we can say that the total pressure will equal the atmospheric pressure, and that'll be the pressure of hydrogen gas in this case, because that's the gas that we're collecting over water, plus the pressure of the water vapor. Okay. And so if you remember the pressure of the water vapor, this is a function of temperature. So that depends on the water temperature. And then this is true. What has to be true about the water levels inside and outside the container in order for the total pressure inside to equal the atmospheric pressure outside?
They have to be the same.
Yeah, they have to be the same. So water levels are the same. Okay, so when the water levels are the same, then we can say that this equation is true. Okay. Oh, and that's question number 3. What must be true about the water levels inside and outside the collection container in order for Dalton's law to apply? They must be the same. Okay. I would prefer that you guys write these in complete sentences though, or at least label it as, you know, Dalton's law of partial pressures or something. Don't just write same. The water levels are the same inside and out. I just don't have a lot of space on my whiteboard. But your background knowledge, either you should write the question and the answer, or write the answer in a complete sentence so I could tell what the question was. Okay. Number 4, what's the theoretical standard molar volume of a gas? So volume of 1 mole of any gas at STP is what?
22.4 liters.
22.4 liters. So again, you would write that in a complete sentence. The theoretical standard molar volume of a gas is 22.4 liters. Or 1 mole of any gas at STP has a volume of 22.4 liters. Okay, and then question 5, we just went over this. Conditions of STP, the temperature is 0 degrees Celsius or 273 Kelvin. And the pressure is 1 atmosphere. Okay, those are standard conditions, STP. Okay, any questions about those background knowledge? Okay, so next you would have these materials. I'd give you a graduated cylinder, a tall cylinder filled with water, a beaker. A eudiometer is something that you haven't worked with yet. A eudiometer, I'm gonna erase this, is basically like an upside down, well, it's like a big test tube. And I guess we use it upside down. And it has volume markings on it. So you're gonna see one in the video I'm about to show you. Okay, but when we use eudiometers, it's basically like a big upside down test tube that has volume markings on it, like this. And it starts at the top. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So that would be 10 mils, 6, 7, 8, 9, 10, 20 mils. Okay, we use it to measure gases because gases are going to go to the top, right? And so when gases bubble up to the top, then we can measure their volume because it's numbered upside down. Okay, and you're going to put this into water. You're going to the reaction would be done underwater. You'd be working with 6 molar hydrochloric acid, which is pretty concentrated. Balance, a barometer. We would look up barometric pressure for the day. I'll give that to you. Metric ruler, magnesium, a rubber stopper, a ruler, scissors, a sink, string, and a thermometer. Okay, so these are the materials you would use. And then if we were working in the lab with this, I would warn you heavily against 6 molar hydrochloric acid is very concentrated. It's probably the most concentrated I'll ever give to you as a student. So anyway, so be careful with if you ever get 6 molar hydrochloric acid. Okay, and so I'll show you, I'm not going to go through every step of the protocol with you right now. You might want to write it down because it'll be nice to have next year in varsity chemistry when I don't give you protocols. But I'm going to show you a video that was done by a few students from a couple of years ago who videoed themselves doing this lab. And you can find this video on the YouTube channel. I uploaded it to our YouTube channel yesterday. So if you go to our class YouTube playlist, this is the wrong one. Here we go. Can you guys still see my screen?
Yes.
Okay, good. So this is it here, the standard molar volume of a gas lab, Foreman and Hefner. This was Noah Foreman and Kylie Hefner. I don't know if you know either of them, but they made this lab. And it's kind of neat. You'll notice at one point they
avoid packs altogether. But sometimes I need
uh-oh. Yeah, try not to make noise behind you. Anyway, they did something with their phone where I think they actually put it underwater at some points during this video, which is kind of cool. So it's about a 3-minute long video that shows you what this lab setup looks like and what it looks like when the lab is running. So I'm going to go ahead and show you that now. Okay. So that was some pretty intense music.
Yeah, I felt like I was watching a cool trailer.
Right? I know. Yeah. So oddly enough, um, Kylie and Noah made me that video a long time ago, years and years ago, prior to knowing that this would be the conundrum that we're in now with coronavirus. And so it came quite in handy to have that so that you guys could see what the lab would look like. So I hope you kind of gathered what would happen. Essentially what we would do here is we would take this UDometer and we fill it. We put some 10 mils of hydrochloric acid in it. We fill it all the way to the brim with water. And then we take a little piece of magnesium. We will find the mass of the magnesium, tie it to a string. And so essentially what we end up with is a little piece of magnesium on a string. There's my magnesium on a string here. And we stopper it into the UDometer. Okay, so we hold it in place with a little stopper there. And then we turn it upside down underwater, and the hydrochloric acid is up here and it starts to diffuse downward. And when the hydrochloric acid gets to the magnesium, then this reaction takes place and the hydrogen bubbles start to rise. And so we end up with these, let's see if I can use a different color. We end up with little bubbles of hydrogen up here. Right, and we're going to line it up so that the water levels inside and outside the UDometer are the same. We're going to have some hydrogen gas up here. And then just by virtue of collecting gases over water, you're also going to have some water vapor up in here. Okay, so there's water vapor. And so we can say that the total pressure inside this container that's been collected, whoa, is the pressure of the, actually let's do this, P total is the pressure of the hydrogen plus the pressure of the water vapor that's collected, okay? And we will line it up so that the water levels are equal inside and out, and then we can say that this total pressure is equal to atmospheric pressure that's pushing on the outside, okay, here. So then we can find the volume of the hydrogen, we can figure out the pressure of the hydrogen gas, we can measure the temperature of the hydrogen gas, and with all of those values, we can figure out the number of moles of hydrogen gas, and from there we set out to prove whether or not Avogadro's law for the standard molar volume of a gas is accurate. Okay, so that is the idea behind this. So let me go ahead and share with you one more thing. I'm going to share with you a data table that was from one of my AP chemistry students when he did this lab this year. So this is the data table. Actually, a lot of you might know him if you're in Model UN. This is Thomas Gherkin data. So go ahead and write down this data or take a screenshot of it or something. This is, you can write it into your lab packet, you can write it into your lab book, but this was Thomas's data for this year. So he measured the temperature of the room, and the temperature of the room is going to be the temperature of the hydrogen gas that we use. So 290.65 Kelvin. He converted that from Celsius for you, which was nice. The water temperature, remember we used the water temperature to figure out the pressure of the water vapor. So the water temperature was even colder than room temperature. It was 288.25 Kelvin. Pretty cold. That's about 15 degrees Celsius, which is about accurate for my classroom. At least that's one good thing. We don't have to sit in that freezing classroom anymore, right? Now you can be in the warmth of your own home. Next, we have the water vapor pressure at that water temperature. So if you were to scroll down to the end of your lab document, you would see the chart where you can match this water temperature to a water vapor pressure. And so Thomas already filled that in for us here. That was nice of him. The barometric pressure on the day we did this lab was very close to 1 atmosphere because we live close to sea level, right? So 1.007 atmospheres. The mass of magnesium he measured and tied to the string was 0.0297 grams. And remember, those AP chemistry students get analytical balances that go out to 4 decimal places, which is nice because you get to use more sig figs. And then when he actually did this lab, the volume of hydrogen gas that he collected was 0.0295 liters or 29.5 milliliters. Okay, so at this point, I'm going to ask you guys, I'm going to break you up into groups of 3 or 4, probably 3. And I'm going to ask that you guys crunch the numbers and go through the data processing together with Thomas's data. And you'll have to use some stoichiometry too. Does anyone need this lab data for more time? Okay, because I'm going to go back over to the lab now and open that up. So once again, remember this chart is used for figuring out the water vapor pressure at the certain water temperature. That's the only reason we take the water temperature, is to figure out the pressure of the water vapor that's produced. Okay. At this point, the observations part of your lab write-up is just bubbling. I hope you guys saw that there was bubbling in the video. Okay. You can also say that the magnesium is a kind of a grayish colored metal. If you look at the rubric, it tells you exactly what to say in the observations section, but definitely the bubbling was evidence of a chemical reaction taking place here. But what I'd like you guys to work through in your small groups right now is the data analysis. So I'm going to break you up into groups, and hopefully you guys can work through numbers 1 through 5. And then we'll come back and we'll talk about these discussion questions. And then your homework this evening is going to be to write a conclusion and evaluation. And then you'll take pictures of your lab notebook or scan your lab notebook and submit those in Google Classroom by tomorrow morning at 8 o'clock. Okay. So at this point, once again, what I'd like you to do is use all of that data I just showed you to answer these 5 questions, and you're going to work in small groups to do that. Okay. Does anybody have questions about what my expectations are for the next few minutes? Okay, cool. If you get put with people that you don't know in your group, be sure to introduce yourself and say hello. And then again, if you're having trouble uploading to Google Classroom, maybe try to troubleshoot with the people in your small group on what works for them. Also, before I forget, we have a birthday in the house today. Sean, I hear it's your birthday. Sean, can I unmute you?
Yeah. Hi.
Oh, there you are. Hi, happy birthday, Sean.
Thanks.
How old are you today?
16.
Hey, Sean.
16. Yeah. All right. Everybody, on the count of 3, you want to do a big happy birthday? I'm going to unmute you. Happy birthday to Sean. Ready? 1, 2, 3. Happy birthday.
That was so bad. Oh my god.
That was
Thanks.
great.
I didn't make everyone sing. That might be even worse.
You're welcome, Sean.
Sean, it's gotta be weird to have a birthday right now, huh?
Yeah.
Anything that you're doing to celebrate?
Not really. We're having like a dinner with family, but
Yeah.
you know.
Well, enjoy. I hope you find a little time to yourself today to do something that makes you happy.
Okay. Thank you.
16, huh? So does that mean you get a driver's license soon?
Hopefully. I mean,
Do you have your permit yet?
no. I haven't been
Gotta get that. When I was your age, and we had our driver's license on our birthday. We would make an appointment with the DMV on
You're
our
not allowed to anymore.
Oh, you're not?
No, it has to be 1 day after 6 months. So even if you do it perfectly timed, you can only get it the day after your birthday.
Oh, you have to be 16 and a half to get a driver's license now?
Like 16 and a day.
Oh, 16 and a day.
Yeah, like you can't get it on your sweet 16 though.
Oh my goodness, why? Well, that's so silly.
Because they're rude.
Yeah, the
I
DMV
don't know.
never anyone's favorite. All right, guys. So I'm going to go ahead and break you up into breakout rooms. And you're going to be randomly placed with a few other people. So, and then I'm going to pop into the rooms and I'll help you. I did try to give you hints throughout this. So in number 1, you're going to be doing some stoichiometry. And number 2, you're using Dalton's law of partial pressures. Number 3, you get to use the combined gas law. Number 4, I tell you exactly what to do. Take calculation 3 divided by calculation 1. And then number 5 is a percent error. So hopefully you guys can work through those and feel pretty comfortable with that. So, all right, here we go into breakout rooms. And it's not working. What's happening? Let's try this again. Nope. Maybe I need to stop sharing my screen first. There we go. Let's try this again. Oh, here we go. Okay, here we go. See you later. All right, everyone, welcome back. So I think most of you were able to make it through all 5 calculations. Does anyone have questions for me about one of the calculations or any of the calculations?
Yeah, I have a question about number 5.
Yeah.
I got a pretty ridiculous percent error.
What was your
It
error?
was like negative 98%.
Something's not right. So Nolan,
Yeah.
let's go through your numbers. What did you get for number 1?
Number 1, I got 0.000122 moles.
Okay, I got that too. That's good. What did you get for number 2?
Number 2, I got with sig figs 0.0125.
No.
I think that's where you made a mistake.
Ooh, bummer.
So it should be atmospheric pressure minus the water vapor pressure. Did you add them together?
Did I? Maybe. I don't know.
I think you might have. So let's see. I'm going to try to draw this back up here again real quickly to make sure we're all clear. Okay, so let's see. Remember we have, I don't know why I erased this. So pressure of hydrogen. We also have some water vapor up in here. And so we can say that this total pressure is going to be equal to the atmospheric pressure because the water levels are equal inside and out. And that'll be the pressure of hydrogen plus the pressure of water. Okay. And we know the atmospheric pressure, 1.007 atmospheres. We know the pressure of the water vapor is a function of temperature, and that should be 0.016993 atmospheres. And so when you subtract, you should get a pressure of hydrogen gas that's 0.990. Do you see that, Nolan?
Yeah. I used the the water vapor pressure instead. Oops.
No, the water. Oh, you wait.
Yeah, I used I didn't use the barometric pressure like at all.
Oh,
I did something completely wrong.
oh, okay, okay. Well, good. Now, hopefully, you know. Now this is what we call the dry hydrogen gas, okay? Because it would be the pressure of the hydrogen without water vapor associated with it. It's like the water's been subtracted out, okay? All right, and then in question number 3 is a little tricky. So let's just quickly talk about question number 3. Question 3 asks you to use the combined gas law, where essentially the initial conditions are our experimental conditions, and then the final conditions are at STP. So we're saying, all right, we've collected this sample of hydrogen gas under these experimental conditions in our laboratory. What if we took that same sample and we applied it to STP conditions? What would the volume be, right? So we've got a pressure that we calculated was 0.990. We're talking only about the hydrogen gas, okay? So the pressure was 0.990. The volume of the hydrogen gas that was collected was 0.0295 liters. The temperature of the air in the room, and you assume that the temperature of the gas inside is equal to the temperature of the gas outside, is 290.65 Kelvin. Then we said, all right, what if we took this sample of gas and we applied it to standard temperature and pressure? 1 atmosphere, 273 Kelvin. What would that volume be? And then you solve for that. And what did you guys get for that? Well, the volume, you should have a small decimal, like a 0.0274 is what I got there, liters. Okay, and then step 4, this is a great example of what I like to call let the units be your guide. Okay, where I'm asking for the standard molar volume of a gas in moles per liter. So you take the number of moles that you calculated in number 1 and you divide it by, I'm sorry, it's liters per mole. I take that back. We usually say it's 22.4 liters for every 1 mole. That's the theoretical, right? So if we take the number of liters divided by the number of moles, that'll give us a standard molar volume. In other words, the liters per 1 mole. So this was your answer to number 3, divided by your answer to number 1 will give you units in liters per mole. And then we can compare it to Avogadro's number. So what did you all get for number 4? Anyone want to speak up?
22.5 liters per mole.
2.5 liters. And so that gives us a very, very small percent error, right? It's almost exactly the same as what Avogadro's hypothesis is. Avogadro said it's 22.4 liters for 1 mole. Our experimental data said 22.5 liters per 1 mole. So I love this lab. I wish we could have done it together, but I love this lab so much that I do it in varsity chemistry and in JV chemistry because it's so good. You can get great experimental results right in our lab to prove Avogadro's hypothesis, okay? So you should get very, very small, less than 1% error. It's a really good lab. All right, so let's just real quickly go back and we're gonna just talk about the 3 discussion questions. Before I do that, sorry, are there any questions about the calculations? Okay, let's talk about these 3 discussion questions. Number 1, why does the acid slowly diffuse downward when the eudiometer tube is inverted? So when you fill this tube up, you have it upright like a test tube, and you put 10 mils of acid and then the rest water. And then you flip it upside down underwater and the acid goes downward. Why does the acid diffuse downward?
Because it's more dense than the water.
It's more dense than the water, exactly. Yep, acid is more dense than water. Number two, two gases are collected in the eudiometer. There's two gases there. What are they?
Hydrogen and water vapor.
Yep, hydrogen and water vapor. Yep, the gas that was a result of our chemical reaction. And then whenever you collect gases over water, you always have water vapor too. And then number three, at the end of this reaction, if the water in the tube were evaporated, which salt product would remain?
Magnesium chloride.
Magnesium chloride. Yeah, magnesium chloride is a salt that's dissolved in there. That was one of the products of our reaction. So we got the hydrogen gas, and then we have magnesium chloride too. All right. Excellent. Okay, students. So at this point, I'd just like you to write your conclusion and evaluation, 2 paragraphs, and then take pictures of your lab book or scan it and then submit it on Google Classroom by tomorrow morning at 8 a.m. And then tomorrow, if you guys would please just start working on that exam review. We'll come back on Thursday. I'll answer any questions you have, and then we'll open up the test for you guys to take. And that's it. That's the end of our gases unit. Okay.
I have a question.
Sure.
For number 1 on the data analysis, there's not really like a formula to like plug into because it's just like the mole highway.
Right. Yeah. Just show me the mole highway. You don't
Okay.
need a formula in words. And if you look at the rubric, it shouldn't say formula in words required there either.
Okay.
Okay. Good question, Riley. Yeah. Just show me the stoichiometric conversion. But make sure you still have a boxed answer with units. Okay. Any other questions? All right, student, that wraps up our session for today. So I'm going to stop recording. Thank you for coming. I hope it helped.
Thank you.